Black holes. Black holes are formed when massive stars die. As a dying star begins to fuse iron in its core, because iron doesn't release any more energy, fusion is no longer capable to counteract the pull of gravity, which causes the star to collapse with a speed of 25% of the speed of light. In a fraction of a second, the outer layers contract, then explode, leaving behind a dead core, which because it doesn't produce any outward pressure, it quickly starts to collapse in on itself, being crushed into an incredible compact region where the pressures are so great that atoms start breaking apart into subatomic particles which push against the collapse violently. At this point, if the mass of the core is under 4 to 5 solar masses, then the forces of the atoms will prevent the star from collapsing entirely, resulting in a neutron star with 20 to 25 kilometers in diameter. But if the core's mass exceeds this threshold, then the atoms won't be able to counteract the gravity, and the core will collapse indefinitely into an infinite small point with no volume, where gravity dominates and spacetime is deformed and warped. The gravitational field is so strong that it distorts the light that passes in and around it. The light that doesn't manage to get sucked in will begin to orbit the black hole in a distortion. If you get past a certain point, an object starts to disintegrate because of the gravity, eventually forming a string of matter 1 to 2 atoms wide, in a process famously named spaghettification, that will fall into orbit around the black hole along the accretion disk at incredible speeds. This spiraling of matter at immense speeds creates a lot of radiation and magnetic field activity, which help us identify them in the cosmos. Through this process, more matter is escaping in one way or another the black hole, the majority of it being spat out from the accretion disk before reaching the event horizon. This event horizon is the black part of the black hole, with enough mass in a sufficiently compact level of space that leads it to form a perfect sphere. After this point, space is so curved that the speed necessary to escape it surpasses the speed of light, being named by scientists the Schwarzschild radius. Between this point and its center, space and time are distorted, with the singularity being the place where all matter has collapsed, a point of infinite density with no real volume or surface area, where relativity and Newtonian gravity start to break down and quantum forces that are not yet understood take over. This singularity is a product of the mathematics of Einstein's field equations that describe it as a boundary of spacetime and a place where time stops. The singularity is not a physical point though, but an inevitable event in the future from where time cannot escape, because spacetime is so curved that there is no more time. In this point, more precisely, time stops forever. Whenever matter or radiation crosses the event horizon, it falls into its singularity and grows the black hole's mass, further increasing the boundary of the event horizon. Where this mass ends up in is an unsolved question of science. The mass seems to fall into the singularity, but the singularity has no volume, being so small. As such, the fate of information inside a black hole remains a mystery. Depending on their mass, black holes are catalogued into 3 categories. Black holes with masses that range between 5 and 100 solar masses, which are called stellar black holes and are the size of an asteroid. Supermassive black holes, with thousands of times the mass of the Sun, that were formed from the collapse of supermassive gas clouds in the early universe, which allowed them to get to their ginormous size. This in turn allowed them to attract from early on groups of stars which eventually formed galaxies. These supermassive engine black holes start at a minimum of 100,000 times the mass of the Sun, and end up reaching billions of times the Sun's mass, being the most massive objects in the universe, with the most powerful gravitational fields in existence. Gravitational fields that behave exactly like any gravitational field in the universe, in the sense that an object can orbit these structures in the same way like in any other system, with the difference being that these objects can grow in mass indefinitely, unlike stars or planets or asteroids. Most black holes observed so far are either small stellar black holes or supermassive black holes. But besides these 2 types, there is another category, intermediate black holes, with masses between 100 and 100,000 times the mass of the Sun. But how these types of black holes are formed is puzzling to science, because the largest stars can only create black holes 150 times the mass of the Sun. A star 130 times the mass of the Sun collapses into a black hole 65 times the mass of the Sun. In stars above this threshold, photons in the core become too energetic in a phenomenon known as pair instability, which morph into electron and anti-electron pairs that generate less outward pressure than the photons. And this makes the star unstable, like in any other supernova. But unlike stars below 130 solar masses, the collapse is so fast that there isn't enough outward pressure to counteract the falling, leading to a supernova that literally blows the star away. leaving no astronomical remnant behind, no neutron star, no black hole, except for one big giant nebula. So basically, black holes above 65 solar masses don't form in a supernova, only through the accumulation of matter and merger with other black holes. But hypermassive stars, at least 200 times the mass of the Sun, do instead form black holes when they die, with at least 120 solar masses, which leaves a gap between 65 and 120 solar masses that is called the Peer Instability Gap. In the case of black hole mergers, this phenomena usually occurs in binary systems and most often when galaxies collide. As the two black holes draw closer and closer to each other, they start to circle one another faster and faster until milliseconds before they collide, when they orbit at a significant percentage of the speed of light. At the moment of collision, an insanely amount of energy is released, equivalent to several thousand suns, in the form of reverberations in spacetime that are called gravitational waves. These waves propagate away at the speed of light over billions of years across the universe, and can be detected from Earth through giant interferometers, with every single one so far being detected either from two neutron stars colliding, a neutron star and a black hole colliding, or from the merger of two black holes. In 2019, LIGO, the giant interferometer, was used to detect these ripples in spacetime through some very sensitive hardware, which picked up four short wiggles that lasted less than a tenth of a second, from the merger of two distant black holes which together had a mass of 150 suns, one with 66 solar masses, the other with 85. But after the merger, they created an intermediate black hole of 142 solar masses, with the remaining 8 solar masses being released after the collision in the form of gravitational waves. This event happened 7 billion years ago, and this object is now 17 billion years away from us, due to the expansion of the universe that happened in the meantime. After more and more data was collected over time about black holes, scientists started to develop theories which included them in the prediction of the universe's demise, with a theory called the Big Crunch that argues that the universe at one point will stop expanding and start collapsing in on itself, contraction due to the gravity of the objects within it. At this point in time, there will be 16 of black holes in the universe that will eventually all merge into one incredibly large, ultra-apocalyptic black hole that will contain the mass of the entire universe and will start to devour spacetime itself, pulling everything into its singularity, and finally ending it. But lately, this theory has been sidelined by others. The study of black holes and gravitational waves has the goal for humanity to eventually develop technology that will permit us to create artificial gravity and allow us to manage and manipulate spacetime itself, and to further understand the many unknowns of black holes. If successful, it will revolutionize the world dramatically, changing the fabric of our society, but until then, more research needs to be done. Okay. Thank you all for watching this video. I hope you enjoyed it, and until next time, take care.